Here we're going to get into something called significant figures, or as I'll frequently say, just sig figs, or even SF. You will hear some places called insignificant digits, and I actually kind of prefer that. It's just not what I was taught or what your textbook uses, so we'll stick with sig figs, but sig dig kind of makes more sense to me. We also have ways that we make measurements. Sig fig ends up affecting how we round when we do calculations using those measurements. Anyway, when we're using any measuring tool or measuring device, we measure using it and we get what are called measured numbers. Measured numbers are a continuum. That is, they can be any range of values between 0 and whatever we measure. That is not the same case for, say, what are called exact values. Money, we can only have exact values. We get in the America, we break things down into pennies, into cents, or into dollars. You can't really have half a penny. I mean, yeah, you can cut a penny and have half a penny, but you can't spend that half a penny. The same thing with the dollar bill, is you can't break up a dollar and have it have that fraction of the dollar's value. It's just a dollar or a $5 bill or whatever it is. Or you can't have a partial number of people. The average number of kids in the American household is going down slightly now, but it used to be 2.5 kids per household. But of course you can't have half a kid. And so what it means is that the average is such that when we do the math, we come up with the 2.5, but that means that most households have 2 or 3 kids, although of course there are some with fewer and some with more, and that's okay. But those we can only get exact values because we can't break it up into a continuum. Those are what are called discrete quantities. As a side note, anytime that we are making a measurement, and that's what the next slide is going to get into, we always have to have the numbers here that are marked there. If there's tick marks, then those are like numbers. It's just usually the tick marks are so tiny that we can't read them, or label them with numbers, and so we just have to count them, and those become part of our measurement as well if they're there. But then we always estimate one place value beyond what the device is marked to do. So this device here is only able to estimate centimeters, or measure centimeters, and we have the ones place, whole numbers here. Yes, theoretically this ruler goes further on and it could also measure out here in the tens place, but the smallest value, the lowest value that it measures is the ones place. We always estimate one place value in addition to that, beyond that. And so because this measures in the ones place, we can estimate the 10th place. And so you can look here and see that this obviously is not a stick that is 4 centimeters long or 5 centimeters long. It's somewhere in between. And so for that in between, we can estimate how far in between. I think it looks like it's exactly halfway in between, so I'm going to put a 5 here. You might look at that and say, no, I think it's a 4. That's okay, it's an estimate. We're going to disagree, and that's okay. In the lab, I'm going to expect your measurements to be like that, and I am going to expect that you are estimating one value. If you measure a volume in a graduated cylinder and it has markings out to the ones place, if you give me an answer in the ones place, it is wrong. It needs to have that estimated value, and I don't just mean afterwards go in there and tack on the 0 or tack on the fake value. I'm going to catch you if you're doing that. Instead, take the time to estimate that place value. Now, on a ruler, those tick marks are frequently tiny. I mean, what's on your screen here, unless you're watching maybe on a phone, this is much bigger than actual 5 centimeters. So those tick marks will be real easy to see. On a real ruler, those tick marks are tiny. And so because they're so tiny here, it can get hard to tell if you're in between or on the line, or how far in between or on you are. And so in that case, pick the middle point, pick the 5, or if it looks like it's on the line, you do have to record it as a 0. And so if it was right on the line here, it would be a 4.0, and that would be our estimated place value because we are measuring that it is on the 0 line. That is part of our measurement. But measured numbers are on this continuum, and they're going to affect how we round in our calculations. Anyway, that's exactly what this slide and the next one says. And so take a moment and read those if you want to, but I'm going to move right along. This one here, different measuring device, and now we have those tick marks in there. And frequently they're unnumbered. And so you have to figure out what is it. Well, when I look here, there are 10 tick marks between 4 and 5, and so that means I'm taking 1 centimeter and dividing it into 10 pieces, which means that each of those tick marks is 0.1 centimeter. Well, now we can actually measure from the markings on the device 4.5. I can see here that I'm between 0.5 and 0.6, and so now my measured part is 4.5, but we always estimate one beyond what the markings on the device do. So the markings on the device here do the maybe higher than the ones placed out here in the tens, but that doesn't matter even if the device goes on, because we want the smallest one. It now has markings in not only the ones but the tenths place, and so then I have to estimate the hundredths place, and they tell us here that they meant for it to be, they probably did take the time to measure it for it to be a 5 there, to be in the middle, but again, that is an estimated value. As long as you have that estimated value, we may disagree on it. One of the best things to do in the lab is you make that measurement, your lab partner makes that measurement, and if you agree on the estimated value, great, and if you don't, then pick the middle ground or check it again or get a third opinion. The other thing as well is using the camera on a cell phone to zoom in on those tick marks is really useful for estimating that place value. So go ahead and take advantage of that. Feel free to do that. As I've mentioned already, if it ends up on the exact place, it is not okay to call this a 3. It is a 3.0. You have to show that you measured that to be the 0 there. Now, I will point out I've been making one mistake here all along, and that is, in addition to having your measurement, you must have units on your measurements. And so they've been doing a good job of doing that. I've been focusing on the measurement parts, which is really what we're trying to teach here, but every measurement you make does have to have a unit. Most of the calculations you do will also have a unit, and that is part of your answer, and it has to be there. When it comes to doing calculations on a test, I will only give you partial credit if you are not rounding properly, if you're not making those estimated measurements, or rounding properly on calculations, or partial credit if you're missing the units. They are absolutely essential to the answer and must be there. On the next one here, we're asked to just measure this. Of course, we'd expect this ruler to go on back this way. So this looks to me to be, there's the 9, we've got 9.1, 9.2, and to me it looks to be right on that line. So I'm going to call that 9.20 centimeters. And again, the measurable part is 9.2, but we always estimate that last digit, and so then that is our correct answer. This brings us then to significant figures, or sig figs, or just SFs here, but it's a way of counting which zeros are important, and that then affects our certainty on our measurements. That also affects the certainty that we can have on calculations then that we do with those measurements. For example, if you are running a 100-meter race, and you are timing using just a amazing electronic stopwatch that is able to measure that it took you 12 point, and let's say that it goes out into the 10,000th place here. That's not reliable. It doesn't matter how precise that is, because there's a limit as to how precise that 100 meters is. It's probably exactly 100 meters, but when you're measuring large distances, it's no longer as simple as having a ruler that's the right length. Yes, we do have tape measures and trundle wheels and other ways of measuring lengths, but there's a limit as to how accurate we can be, how certain we can be about that, and because of that, it doesn't matter how precise our timing is here. If we want to figure out your velocity there, that 100 meters is going to limit how certain we can be based off of the more precise time. This number here is more precise, more exact, but it doesn't matter because the uncertainty we have on this, let's say it's 1 meter plus or minus even just 0.25 meters. Well, it turns out that if you do this as 100 0.25 divided by this number, or you do it as 99.75 divided by this time number, you will get drastically different speeds, and you'll find out that they're only accurate out and only agree with one another out to about 3 places, which is how big that 100 is. And so because of that uncertainty, we measure using something called significant figures and round using significant figures. There's a whole bunch of rules for them. Those rules are really just about determining what numbers are important or unimportant in a measurement, and therefore in a calculation that we do with those measurements. The other option, as a side note, is to do this uncertainty thing here. The problem is this uncertainty compounds. It starts to get worse the further along you go, and doing the math gets really hard and really obnoxious. I had one lab in college where they were trying to emphasize why sig figs are important, and so they had us do this. But for example, we had a uncertainty on a distance, like let's say that 100 meters, where the measuring device that we were using, it had uncertainty in the centimeters range, and so we could be off plus or minus 5 centimeters, or plus or minus 0.05 meters. And there was uncertainty based off of the fact that we had to estimate that last value. And so when you're estimating that last value, you got an estimate that causes you to be off by plus or minus whatever you estimated there. And so these end up compounding, and you end up with a plus or minus 0.055 is how much our measurement could have been off. And then we had to go through and do this exact thing where we did the calculation with both of those, and then we got an answer, and we had to use that answer in another calculation. And so then we ended up with a plus or minus range on that answer, and then when we do the math again, you get a plus or minus range, and it just gets to where it's complicated. And the whole point of that was to tell us, look, sig figs is better, use sig figs. If it's just a number, everything's important. And so we just count the number of figures, or the number of digits, the number of place values in there. And I like to think of it as place values. And so there's 2 place values in the first number there, there's 5 in the next one. If the 0 is in the middle, it's of course important there. It's part of the measurement itself. And so then those are significant. There is a typo on this next one here. There should be a decimal there, because a 0 at the end of a decimal number. 50.0 does have 2 sig figs. 50, it turns out, as you'll see here in just a moment, does not have 2 sigs. It only has 1. This one here, these zeros, they wouldn't have been written if they weren't important. I go back to thinking about money a lot when I'm trying to do estimations and calculations, or when I'm thinking about things like significant figures. If I'm saying I have $1, I'm saying it's exactly $1, and not some fraction there. And so those zeros are important. Gas stations will tell you that the price of gas is, say, $3.49.9, and for you, that extra a thousandth of a penny doesn't matter. But when they're doing lots of sales in a day, it starts to add up to be hundreds, even thousands, or tens of thousands of dollars at a single gas station in a day. By having that extra little thing, there's also some psychology to having the number be that. I mean, there's a reason why stores sell things for like 99 or 98 cents, and you even though you're like, no, that doesn't trick me, I'm going to round that up to $1. Psychologically, we have studies that show that actually, no, that's not always the case. You don't do a good job of that, and you end up fooling yourself into thinking it's less than it actually is, because a lot of times we drop the pennies rather than doing the rounding properly in our head. Anyway, those zeros wouldn't have been written if they were unimportant. Here, again, when there's no zeros, or when the 0 is written at the end of a number, it is important, and so those count. Where zeros start to be unimportant is when they begin a number that's after the decimal. Those are all unimportant. As a side note, it's standard practice to write the 0 before the decimal just to lock in and make sure that it's clear. It also helps you see that decimal point there to realize that this is a decimal number. If you start out with the decimal, it can get confused with the period, of course, and so we'd like to start with that. And so then here, the only numbers that are significant are the numbers in there. Now, we could combine that if we had 0.0750. These leading zeros are unimportant, but the 7, the 5, and that trailing 0 are important. So this number that I wrote here has 3, because we're kind of combining this one with one of those rules up there. The other way it's not significant, and why that decimal on this 50 was important, is because these trailing zeros are not important. And so then this one here, only the 85 are, and only the 125 are. Excuse me, not that 0. I looped in too much there. That's just a pen problem. And so we only have those 3 numbers there as being significant. One shortcut, and this is going to get ready to get into that, is if you write things in scientific notation where we drop unimportant zeros, then because we're already dropping the zeros with that, then you end up focusing on just the significant figures. It's a quick shortcut for figuring it out, and to be honest, it was someone teaching me that when I was fairly late in college. That sig figs kind of just clicked all the way for me. Turn it into scientific notation, and then anything that's left is important. The only time that causes problems is when you have something like this one here. That original number would have been, or let's say that was a positive 3 there. That original number would have been 570 with the decimal there. When you turn that into scientific notation, it's tempting to make it 5.7, but it's actually 5.70 times 10 to the 2, because that 0 was significant in the original number because it was locked in by a decimal. That locked in by a decimal rule is the weirdest one for you to get used to. Pretty much everything else here hopefully makes quick sense, and you'll get plenty of practice over this. And I will say I grade sig figs throughout the year, but it's a minor part of the grade. And so if you just ignore it, you're going to lose points and maybe half letter grade, whole letter grade, but it's not going to absolutely kill your grade if you don't get this down. Hopefully with enough practice, that won't be an issue. The next several slides just go through each of those rules and gives you more examples with them. Because it's a little bit of a strange concept, I am going to take a little bit more time here, but I won't dwell on it too much. So pause, take a moment, read, make sure that you do understand everything here. But first off, if it's numbers, they're important. Sig figs is all about determining which zeros are unimportant, or which numbers are unimportant. They're always going to be zeros. So if it's just numbers, they're all important. If the zeros are trapped inside of the number here, then they're important. And so then all of those are important. We have 4. All of those are important. We have 3. However, here, the leading zeros are unimportant. If you could get away with not writing this 0, which of course you can, then it's definitely not important. This one here is what we call a placeholder, and that is, it is holding a place value, but we didn't actually measure it, because keep in mind, measurements are building things up. If we're coming up with a tiny measurement like this, I'm going to go with a more chemistry example of grams. If we're using a really precise scale and you're using a very fine powder and you're slowly adding that power, you're starting with 0 with an infinite number of zeros there, and you're building up to some number. Well, if you have 0.07 something grams of it, you haven't got to 0.1 yet, and so you've not measured that 0. You're building up from 0 and you've not hit it yet. It's just like if this number was 0702, we've not hit 1,000 yet. We're counting up to there, but we haven't hit there, and so of course that's not important. We haven't actually hit it yet. We've not measured it yet, and so we get to ignore that 0. Here we get a little bit of a mix. We have some, well, this one we had a trap 0 as well. Here we have a whole bunch of trap zeros, well, I guess 2 trap zeros, and only the leading 0 is unimportant, so 5 there. Again, here when we have decimal numbers, they're significant. This one here, they are significant. It's 4. Now the textbook here has 200 minutes. They are saying that is 3. I have always taught, I have always thought, I have always been taught and always read that to emphasize, or to even say that 200, that those zeros are important, you have to lock it in with the decimal, or you have to write it out in scientific notation where they become these trailing zeros that are significant. Without that decimal, I would argue that that only has one sig fig. As a side note, when you have something like 200 and you want to show that the tens place is important, but the ones place isn't, a measurement with, say, a beaker would do this, then there's two ways to do that. One is to put a bar over the zero. That doesn't mean repeating, because it doesn't make sense to have a repeating number in the middle of a number. Or, again, scientific notation 2.0. I suppose on both these I should have shown the 10 to the 2. But, again, I would read this as having 1. Having said that, because we're dealing with the textbook and because some of you will be doing online problems, you probably need to hold that tension in your head and imagine that when you see a number like this, imagine that decimal to be there and count it as 3 sig figs. I would personally disagree with that, and I will make it very clear on any problem that I make up in an assignment that it is important by putting that decimal in there when I want it to be important. I tend to not do the bar thing. I will write it out in scientific notation if I need to indicate something like that. Again, beginning zeros, unimportant, which we kind of saw on a prior example, as well as beginning zeros before we get to digits, because again, you're building up from 0 to this number, and so we haven't hit those higher numbers yet. This trailing zero wouldn't have been written unless it was important, so this one does have 3 digits that are significant. This one only has 2, and this one only has 1. And again, right here, this is why this disagrees with that 200 example that they had, because they're saying that those are unimportant. Well, why would they be important on 200 but not important here? It's because it has to be locked in by a decimal. I'm hoping that that is a typo and not a mistake the textbook has throughout. But 2 significant digits here, 2 here, and that is not 3. Yes, it is. That's a 0 there. I looked at the comma and said, oh, ignore those. But that is 3 because that's also a 0. That is unimportant. So 3 digits there. Here, the zeros wouldn't have been written, and scientific notation is easy because when you have scientific notation, everything that was written is important. Keep in mind that this is a way of shifting the decimal. It is not a number. We don't count that 1 0 or the power as being digits within the number. The number is the thing before the times 10 raised to the. And so then we have 3 sig figs, 2 sig figs, and 5 sig figs. And so, again, they're trying to show the way to compare regular measurements to scientific notation. Scientific notation is the easiest way to figure out significant figures. I know it's annoying to take a normal number like 0.3 or 500 and turn it into scientific notation to count your significant digits, but it does matter. And does make things simpler to count your significant digits. Here, all 3 of them are. Here, only the 4 is. And here, the 3 and the 0 are, because that 0 wouldn't have been written, but that 0 is not necessary. So coming into here, look at the number of significant zeros, unimportant, 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 1, 2, 3, and then that 0 is important, so 4 sig figs there. Here, that 0 is in the middle, so it's important, which means everything is important, so 1, 2, 3, 4, 5 sig figs there. And again, this is a trap 0, so it is important. The 1s and the 4s are important, but those trailing zeros are not, so then there's 4 sig figs on that one. I mentioned this already, but here's the slide on it. There are such things as exact numbers. I don't love the cookies example here because you can break a cookie, but you understand. If you go to a store to buy cookies, you don't buy a fraction of a cookie, you buy cookies. And so those are exact numbers. When we have exact numbers, there isn't really sig figs with it. What is strange here is these here are exact numbers. Our conversion factors are exact numbers. And the reason exact numbers are important is because we can be certain of those measurements and we don't worry about the sig figs they have. The way that I always describe it is you can imagine them to have an infinite number of important zeros afterwards. And so because of that, everything there is significant. The other ways you can word that is, 1, don't let conversion factors limit you. I recently heard another teacher suggest something different than what I was taught. I was taught the infinite number of zeros and just don't let it limit you, depending on which instructor I had. But something that someone else suggested is if you have a mass that you measure, say you weigh out 3.79 grams of carbon, and we'll get into doing calculations with this, and we'll use what's called a conversion factor, but it turns out that there's the mass on the periodic table for carbon is 12.01 grams, and it turns out that's equal to something called 1 mole. We'll get into how to do these kinds of calculations later on, and we'll get into what the heck a mole is later on. Don't worry about those now, just trust me for the purposes of the example. Well, since this here has 3 sig figs, what I should do is I should make sure that my conversion factor has at least 3 sig figs. If it has 3 sig figs, then I know that this isn't going to limit me because I have the same. Or make it have more sig figs, at which point we always round using the one that has the least anyway, it turns out. And so since we round using the one that has the least, this one has less than that one. It's a really great trick. I really like it, especially for some of the giant constants that we end up having. Okay, it makes way more sense to me. Like, how many digits should I take pi out to when I'm doing a calculation? You've heard of pi before, 3.14. 159 is all the more I have memorized. I used to know it out to more. I've never cared to learn it out to a lot because it never stops, and it's not worthwhile because it gets rounded off in calculations that you do. And so why worry about knowing it? But if you're doing a calculation where, say, you have 4 sig figs, well, then maybe you want to come out to 3.142 there so that it matches the number of sig figs you have in your measurement. And so that was just a useful trick. I kind of like it better, and I think I'm going to permanently teach it that way as we go on. Anyway, this here is just the same thing, but what it says here is exact numbers do not have a limited number of significant figures, and so then they don't affect anything that we do in a calculation. So getting into some practice over this here, this one wants to go exact or measured, so this one is exact. This is measured, and this is a conversion figure, so it's also exact. These are what are called discrete quantities, as I mentioned earlier, and this is a conversion factor. Discrete quantities and conversion factors are both exact. Here, just more practice over sig figs. So again, not important, 2 sig figs. All of those important, 3 sig figs. Leading 0 is not important, 1 sig fig. This here wouldn't have been written unless it was important, just like these two up here, and so 3 sig figs on all of those. This one here has us doing kind of the reverse process. Which one of these has 3 sig figs? So this one here has 3 sig figs. Which one has one where all the zeros are important? It turns out it's 2 of these. I suppose I should have circled my answer there. All the zeros are important, and which the number of sig figs. So I guess this is like the other questions I've been answering. All of these are important because that 0 wouldn't have been written if it wasn't important, so 3 sig figs. I will leave it to you as extra practice or a challenge to count the number of sig figs in each of those. Good practice to give yourself extra questions. Anyway, that finishes up this section.